So today's lecture is a continuation of our previous lecture on electrons, energy levels, atomic orbitals, electronic world configuration. They'll fill in the word orbitals. So a useful way of representing electronic configuration is a diagram that places what electrons what in boxes. And each box represents what an atomic what orbitals. Now there are principles involved. That's what we call the Pauli exclusion principle. It states that what no two electrons can have the same 4 quantum numbers. So orbitals can hold a maximum of 2 electrons, provided that what they spin what in opposite direction. So this is an orbital, which is this is an orbital. We are using a box diagram to represent an orbital. We say an orbital is a region or space where one is likely to find an electron. It can be defined as what a 3-dimensional statistical shape where one is most likely to find an electron. So we use box to represent what are orbitals. So orbitals can hold a maximum of 2 electrons, provided that they spin in opposite direction. So they must spin in opposite direction, which is this, or it can be like this. So this is how you represent it. You can represent it like this, or you can represent it like this. So you can use this form or this form, but provided that they spin in opposite direction. Just the one we have here. This is 1s2, 2s2. This is 2p. So they must spin in opposite direction. So you have to follow the Pauli exclusion principles, that an orbital can hold a maximum of 2 electrons, provided that they spin in opposite directions. Now, in filling the orbitals, there are rules we have to follow. Consider the first rule, which is the Pauli exclusion principle. Now, the second rule we want to consider is the Hund's rule. Now, what happened in filling the orbitals? When the number of electrons is equal to or less than the number of orbitals, when the number of electrons is equal to or less than the number of orbitals, then the electrons occupy separate orbitals. Now, these electrons are shown all pointing up. Only when the number of electrons exceed the number of orbitals are they shown as as paired. So what is Hund's rule trying to explain? That orbitals of the same energy remain singly occupied before pairing up. So this as a result of repulsion between electron pair. Let me take, for example, if we have nitrogen or oxygen. Let me use oxygen for example. Oxygen, the atomic number of oxygen is 8. So if we are to represent the electronic configuration in an orbital box diagram, it will be 1s2, 2s2, then 2p4. So you fill 1, 1, 1, then you pair. So you fill it singly before you start pairing. For example, this is 2p5. So you fill 1, 2, 3, then you come back and pair 4 and 5. So that is the Hund's rule. Orbitals of the same energy remain singly occupied before pairing up. And this is due to the repulsion between electron pairs. So in arranging electrons, you have to follow the Pauli exclusion principle and also the Hund's rule to get the accurate result. So please, I want us to understand and know this very, very well and follow the rules when writing electronic configuration and when filling orbitals. So we are looking at the electronic configuration of the transition metals, transition elements, which are elements with partially filled d orbitals or elements with incomplete d subshell. The transition metals, they are in between group 2 and group 3. They are generally called the d block elements, and they are all metals. Now in transition metals, what happens? The 3d and the 4s subshells are very close in energy, which leads to some anomalous behavior. Other transition elements will follow the Aufbau principle, the Pauli exclusion, and the Hund's rule in writing electronic configuration. It follows generally the building principle, which is the Aufbau principle, whereby you fill electrons starting from the lowest energy level that's available. So in transition metals, there is an anomaly, there's an anomalous behavior as a result of the closeness of the 3D and the 4S subjects. They are very close in energy. So it leads to what? Some anomalous behavior. And one of them is that the first one is what? Because of the stability of the half full and the totally full 3D subject, there are two exceptions to the Aufbau principle. There are basically two exceptions to the Aufbau principle. If you are writing the electronic configuration of the transition elements, they follow what? They follow the normal Aufbau principle, they follow the normal word pattern. So the two exceptions to Aufbau principle is between chromium and copper. Between what? Chromium and what? Copper. In chromium, the 4s, in chromium, the 4s is half filled, and in copper, the 4s is also what? Half filled. These are the only exceptions in the first row what? The first row D block element, which are the transition what? Elements. And the second anomalous behavior is that what the 4s electrons are ionized before the 3D. So electron leaves both the 4s and the 3D, but the electrons leave the 4s before what? Before the 3D. That is why we say transition elements, they have variable what? Oxidation state. They have variable oxidation state. They can easily change their what? Oxidation state. So this is because the ordering of the 3D and the 4s orbital energy is reversed in cation. So the 4s and the 3D, they are also involved in the ionization process. Electron leave the 4s before what? Before the 3D. For example, if we have iron, for example, which is a transition element, if we have iron, for example, iron is 26. If we write the electronic configuration, it will be what? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d6. But if it is ion 2, that means there's loss of 2 electrons, which is 24. So it will be 1s2, 2s2, 2p6, 3s2, 3p6, then 3d what? 3d6. You see that there's loss of what? 4s or electron in what? Ion 2. Then if it is ion 3, you can also write for ion 3, which is Fe3 plus. There's loss of 3 electrons, which is 23. So it will be 1s2, 2s2, 2p6, then 3s2, 3p6, 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 then 3d5. So there's loss of what? 2 electrons for the 4s and what? 1 electron for what? The 3d, which is 3d what? 3d5. So 4 will be out of what? Out of it. So electrons leave the 4s before the 3d. So electrons leave both the 4s and what? And the 3d. But they leave the 4s before the 3d. It's as a result of what? The anomaly that occur as a result of what? The closeness of the 3d and the 4s was sub-shared. So if we're writing the electronic configuration of the transition element, we need to consider chromium and copper, which are the exception, and we need to consider what? That the 4s electrons are ionized before what? Before the 3d. So looking at the electronic configuration of chromium, which is an exception to the Aufbau principle, which is part of the anomalous behavior of what? The transition element as a result of what? The closeness of the 4s and the 3d and the 4s. So what happened is that what? The chromium, the 4s is half filled in chromium. In chromium, the 4s is what? Half filled. And this is because spatial stability is assigned to half full and totally full D orbitals. And so if following the normal Aufbau principle, one would expect the electronic configuration of chromium atoms to end in 4s2, then 3d4. No. The reason is because spatial stability is assigned to 3d, to half full and what? Totally full d orbitals. So to achieve a more stable arrangement of lower energy, one of the 4s electrons is promoted into the 3d to give 6 unpaired electrons with lower repulsion. Chromium, for example, if you are to write the electronic configuration of chromium, chromium ion, which is 3 plus, that means there's loss of what? There's loss of 3 electrons. There's loss of 3 electrons, so the electronic configuration will be what? 21. So if you have to write the electronic configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p6, and what 3d what 3d3. So there's loss of 1 electron from the 4s and 2 electrons for the 3d. So electron leaves the 4s before the 3d. So these exceptions as these exceptions as a result of the fact of the closeness of the 3d and the 4s subshell. They are very close in energy. So please, I want you to take note of that. It also occurs in copper and in what chromium. We're going to look at that of what copper. So the same process for copper, which is part of the exception as a result of what the closeness of the 3d and the 4s subshell. So there's an anomaly. There's an anomalous behavior whereby what the 4s is half filled in copper, and the reason is because special stability is assigned to half full and what totally full d orbital. So in copper, the d orbital is totally what filled. So one would expect the electronic configuration of chromium atoms to end in 4s2 3d9. So to achieve a more stable arrangement of lower energy, one of the 4s electrons is promoted into the what 3d. So to give you what a totally full d orbital. So spatial stability is assigned to what half full and what half full and totally what full d orbitals. So if you look at the transition element, the copper is what? Copper is 29. So let's say copper 1 ion, if I to write the electronic configuration, which is what? Loss of 1 electron, which is 28. So it will be what? 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 3d what? 3d10. So electron leaves the what? 4s. So electron will leave the 4s before what? Before the 3d, which is part of what? The anomalous what? Behavior. The 4s is ionized before the what? Before the 3d. So if we have copper 2 ion, which is Cu2 plus, which is what? 27. So it will be 1s2. Then you have 2s2. Then 2p6. Then 3s2. Then 3p6. Then what? You have what? 3d what? 3d9. So one electron leaves the 4s, and also the other electron leaves what? The 3d or 3d. So electron will leave the 4s before the 3d. That's why transition metals, they have variable oxidation state, because the 4s and the 3d, they are involved in the ionization process. Electron leave both the 4s and what? And the 3d. Like in copper 2 ion, one electron leaves the 4s, then one electron leaves the 3d to give what? 3d what? 3d9. So it's as simple as ABC, and please take note of what? Take note of the exceptions from the Aufbau principle, which is in writing the electronic configuration, and which is between what? Chromium and copper. So this is a summary of the shells, the subshells, atomic orbitals, electronic configuration. So if you look at the table that we have here, so you have the number of shells, number of orbital, the subshell name, the electron holding capacity, that is the maximum number of electrons it can hold, the electronic configuration. So let's look at the number of shells. The first shell, the first shell number of orbital is 1. Then the subshell name is 1s. Electron holding capacity is 2. So the electronic configuration is 1s2, just like that 2. The number of orbital is 1 and what? 1, and number of subshell is 2. Number of orbital is 1 and 3. So the subshell name is 2s and the 2p. The electron holding capacity is 2 and what? 6, which is total of 8 electrons. We have 2s2 and 2p6. Then the name of subshells, we have 3. Then the number of orbitals, 1, which are the 1, 3, and what? And 5. So we have the 3s, the 3p, and what? The 3d. Then the electron holding capacity is 2, which is the 3s can hold 2, the 3p holds 6, and the 3d will hold what? 10. So the electronic configuration is 3s to 3p6, 3d10. Then the number of subshell, which is the first subshell, number of orbital, you have 1, which is the 4s, 3, which is the 4p, 5, which is the d, and 7, which is the what? The f. Electron holding capacity, the s will hold 2, p will hold 6, d will hold 10, and f will hold 14. So you write the electronic configuration: 4s2, 4p6, 4d10, and 4f what? 4f14. So it's as simple as what? ABC. So this is a summary of the whole what? Of the whole process. So please, I want us to go through and get the best out of this lecture, And please feel free to reach out to me if you encounter any difficulty. I'm Mr. Joseph, your chemistry teacher. I'm always there for you. Please subscribe to my YouTube channel. Make sure you like, make sure you share, and comment and share. So thank you very much for listening. I'm Mr. Joseph, your chemistry teacher. I'm always there for you. Thank you very much. I'm Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel. Thank you for listening.